Hey folks, how you doing? Professor G here, and today we're going to talk about the history of astronomy. So, we've been staring at the stars for as long as we've existed, I think. And in geology class, I always talk about our early observationists instead of early scientists. Um, we've been paying attention to things much longer than I think this has been sort of an organized sport, if you would. Um, at some point, we transitioned from amateur to professional, if you would. And so when we start this conversation about the history of astronomy, as your book indicates, these folks are by no means the first people to think about this stuff. Um, you've got, only to look at Stonehenge and a handful of other features around the world that are unbelievably ancient to realize that we've been noticing this stuff for a long time. But these folks that we talk about in this PowerPoint, these were formally trained, et cetera, et cetera. Um, and as you see, their ideas, as you will see, their ideas weren't always right either. But I always get asked, why do I, waste your time telling you about people that weren't right? And unfortunately, that's part of the nature of science. Going back to our very first lecture this semester, we learn stuff as we go along, and we understand and we realize things. Um, Sometimes we forget what we already knew, okay? But it's a learning process. So, anyhow, point being, we started off here, at least officially in science, with this geocentric model, geo Earth, centric center, and the idea that the Earth was the center of everything. A little conceited of us, of course, but we had every reason to think so at the time. So anyhow, it was the idea that the sun, the moon, the stars, um, all revolved around us, and it kind of looks that way. If you stand on the earth and just watch things for a while, which again goes back to my early observationalists um, words there, that's kind of how it looks. Um, some other ideas that we'd held on to for a long time. I think it was Aristotle, might have been Plato, had the idea that a circle was deemed the perfect shape. So once we realized the difference between stars and planets, we assumed that the planets all rotated in a circular uh, shell around us. And speaking of shells, the stars. Okay, and I'll refer to this over and over again. I always call it the planetarium effect. You've hopefully been to a planetarium at some point in your life. You sit down in that chair, you recline, you stare up at the ceiling, and every star that they show you, everything that they show you, is on the same plane, if you would. Okay? Um, and when we look up at night, you've got no reason to assume that these stars aren't all in the same vicinity of one another. That's one of the first things that shatters all of your young preconceived notions when you learn a constellation and you're real proud of it, and then somebody comes along and says, well, the stars in Orion are nowhere near each other. That one is 5 million miles farther back than the left shoulder than the right shoulder, and so on and so forth. But we see this. It's how our brain functions or processes this stuff, that we do have a ceiling above us. And so understandably, that's how our situation started. It wasn't long, though, that we realized that the geocentric model had some issues. We go back to Ptolemy in Egypt, and he, not only had free time to stare up at all this stuff, he may have very well been employed to look to observe this stuff, but he also had some schooling, some background. He's a mathematician, as you see here in this slide. And what he realized was that some of the planets, the word is retrograde, they sometimes move backwards. Okay, and well, that didn't really work out. And the Ptolemaic model, as it's called, still has a geocentric basis to it, but it was the beginning, again, even though geocentric was wrong, it was the beginning of realizing that something else, something bigger is going on here. He's like, okay, wait a minute, if this is going to work, we've got to do this. And I don't think I have a slide for it here, even though I just made these 2 days ago. No, I don't have a slide for it. Your book will show you that he came up with these crazy little loop-de-loops that the planets would do, and there's a vocabulary word for it that you don't need to worry about. But in order to compensate for it, this observation that he made, he had the planets doing these little loop-de-loops within their orbits to match up with what we actually saw. And again, while that seems so silly right now, it's science. It's a process. It's thinking. Okay. So I'm not going to bother you with his Ptolemaic model, but just understand that it's a step along the way. Just looking at my notes here. So the stars, generally speaking, and the stars move across the sky in an east to westerly fashion. Okay, from the east to the west. Hopefully you realize the sun does that as well. The sun is a star. All the stars move, apparent movement in the same direction there. All right, moving on to Copernicus here. We're 1473. What were we? Oh, we were 90 to 186. So probably he came up with this stuff towards the end of his amazingly long life for that early in the world there. Good 96 years old. Probably middle to end of his life is when he came up with this stuff. So we're jumping from, a good 1,000 years easily to Copernicus. Heliocentric. Helios, the sun. Okay, this is not a new idea. It had been floated many times. Different folks, different cultures, but geocentric just kind of reigned supreme. So supreme that that speaking out against it was heresy. This is something that they like to push in the high schools and everything about him and Galileo. They couldn't speak out against the church and science versus, this is like the beginning of church versus science, really. So at any rate, he put forward this idea that the Earth wasn't the center of everything, that it was, in fact, the sun. Speaking of Galileo, not too much longer after Copernicus here, Copernicus died 1543. Galilei was born in 1564. By the way, please, I am never going to ask you these dates, okay? This is simply for timeline stuff, just to give you an idea how the thought process is moved. I'm not going to quiz you about when, who did what. Galileo was amazing, okay, on many accounts, but in this context, he was the first person to use a telescope to look up. Okay, at any rate, the first person to get published doing so. And one of the neatest things that he saw, one of the planets we acknowledged, one of the planets we could see, more about that in a later lecture, he saw that Jupiter had moons, satellites orbiting it. And from that, he rationalized that not everything out there orbits the Earth. If something could orbit another planet, then maybe not everything orbits the Earth, and again, that's how these ideas start. Kepler, all right. Kepler, I don't want to call him a physicist, but he went out there with some pretty interesting ideas on planetary movement. 1 second here, folks. Back. So, Kepler and planetary motion. First off, he gave us the idea that planets orbit in ellipses, not circles. So, if you've ever drawn a circle with a compass, which I'm sure you have, that pokey little metal thing with a pencil attached to it that always slides out and makes your circle go wrong, and at least the cheap ones you have at school there. You understand the idea of a circle. You have a center, one center point, okay? In ellipse, there's two center points, as strange as that sounds. And we're not going to get into geometry. You don't need to worry about it any more than that. But they call them foci. There's two focuses, two foci. All right. So, anywho, his first law says that every planetary orbit is an ellipse. It's elliptical, not circular. And the sun is only one of the foci. His second law states that a planet's orbital speed changes throughout the year, fastest at perihelion and slowest at aphelion. That's technically not what his law says. You're welcome to read his law in the textbook. It talks about sweeping out equal movements of time in increasing distance. There's my distilled version right here. It's basically that a planet's speed varies based on its distance from the sun. We've got two words here, perihelion and aphelion. Okay, peri and ap. Helio refer to the sun, of course. Okay, so perihelion is when something is closest to the sun, and aphelion is when it's farthest away from the sun. Remember, these are ellipses, not circles. So at some point, even the Earth is closer to the sun than at other points. Okay, this is possibly because I stretched out the image to make it take up more slide space here. This is probably much more elliptical than it was meant to be. But this is sort of an egg-shaped orbit here. But at any rate, the idea is that when the planet is closer to the sun, it moves faster than when it is slower, than when it is farther away from the sun. And that is Kepler's second law in a nutshell. Kepler's third law, excuse me, makes plenty of sense, I hope. If nothing else, we can boil this one down to the car racing culture. Okay, planets farther from the sun have longer orbital periods than those closer to the sun. In other words, it takes longer. The farther you are away from the sun, the longer it takes to go around it. And just looking at this diagram, I hope you realized that. Okay. And again, I referred to the car culture there. Think about on a given NASCAR race or a horse race or whatever. If you're on the inner circle, okay, the inner part of the circle there, you've got a shorter trip than someone in the outer lane. If someone in the outer lane wants to beat someone in the inner lane, they've got to go faster, right? Because they have more distance to cover. So, we would expect that the farther out a planet is, that its orbital period would be longer. An orbital period being the amount of time it takes to make one lap around the sun, by the way. All right. Again, your book goes into details. It starts talking about semi-major axes and whatnot. If you're interested in that kind of stuff, feel free to dig into the dirt there. But just based on this diagram here, you see that Mars is a good, what do we call that, 75 million kilometers farther away. And as such, its orbital period is not quite twice as long, but a good bit longer than ours. Mr. Newton. All right. Talk about a guy that dabbled in everything. Here it is. Those of you struggling with calculus, you got him to thank. Those of you who enjoy rainbows, you've got him to thank. He didn't create rainbows, but he kind of explained what's going on there. He perfected a new type of telescope, one that's still used to this day, a reflecting telescope, as opposed to I believe it was the refracting telescope. The problem with the refracting telescope was kind of how he figured out the whole color spectrum thing there. It was messing with the light as it was coming back through, so he made a new type of telescope. Okay, he didn't like the data he was getting, so he made a new machine. In addition to all of that, he gave us the law of gravity and 3 laws of motion. Okay, so in addition to Kepler's 3 laws, now we've got Newton's 4 laws here. There were a variety of images of him. I liked this one. Some were more austere than others. Some were just downright silly, and some were these classic Greek iconic statues. But this one looks real. I don't know. I like it. So I didn't bother explaining the law of gravity to you. At least I don't think I did. Oh, there it is. I guess I do. But I started with Newton's 3 laws of motion, I suppose. Sorry. We got inertia, acceleration, and we'll call it equal and opposite. And I see some wonderful typos here. I was going to correct the lack of bold printing, which I'll do as well. But there's also some typoing here. So inertia. Okay, an object at rest remains in rest. You've heard that. An object in motion remains in motion. And here's the thing, and we say discover. Okay, he didn't make these things true. He observed that they were true, and he made some rules about it. And that's what these folks do. They acknowledge things that already exist, and we see it in geology a lot. Okay, Earth science, we try to talk about it when we can, but you know, they're just, somebody has to point it out and be the first person to say, hey, this is what happens, and then they get the rule named after them. So it's not like this didn't happen until Newton said it did. So anyhow, the idea of inertia. He gave us the word inertia, let's say. So unless a force acts upon it, an object will remain sitting still or moving unless you do something to perturb it. All right, acceleration, related. Okay, when a force acts upon a mass, it causes an acceleration. An acceleration could be viewed as a change of speed, which is how we usually think about it, but also direction. And this gets into the difference, if you've had any physics under your belt, when technically speaking there's a difference between speed and velocity. Okay, this is sort of the same kind of realm here, but you could get an acceleration just in a different direction than something was moving, but a force has to act upon it. And if you remember this kind of stuff, we're looking at the F equals ma. Remember those formulas? All right, force equals mass times acceleration. Good stuff. So anyhow, and then the last one, every action has an equal and opposite reaction. This one's kind of hard to, we've heard it before, but I'd almost say this one's kind of the toughest for folks to swallow. The example in your book, I think, was a baseball bat hitting a baseball. Okay, and the idea that the pitcher throws the ball, you hit it with your bat is accelerating forward, it makes contact with the ball flies out of the park. Well, why doesn't the bat fly out of the park? Well, you're holding on to it very tightly, ideally, but that energy is absorbed. Okay, so not just the ball flies out of the park, but the same amount of energy that caused that ball to fly out of the park was actually present in the bat for a moment as well. Okay, and you absorb that into your hands, into your arms, so on and so forth. Or if you let go of the bat at just the right moment, I suppose it would fly backwards as well. So So Newton's laws of motion, it's just foundational material right now. Please don't get too stressed out. I've used the word physics a few times. This is entry-level earth science here. So, I'm not going to have you balancing equations and all that jazz. Don't worry. But we need to acknowledge it. Speaking of which, gravity. All right. Gravity tells us that an object attracts all other objects to it. Simple, but there's more to it, unfortunately. The more massive the object is, the more attraction it has. Mass and gravity are directly connected. Okay, the more massive an object is, the more gravitational pull it has, and the more it's affected by other gravitational pulls as well. Okay, and again, there's some equations behind all this. We're just not paying attention to them. And then here's another aspect of it. This one gets kind of glossed over a lot. The closer the object is, the stronger the attraction is. Okay, so not only is it related to mass, but it's related to distance. So gravitational force increases with proximity, if you would. All right, and from there we drop to modern. You see I have that in quotes there. What are we talking about? We're talking about 18th, 19th, and into the beginnings of the 20th century. We have this conversation again over and over and over again. Primarily when I talk about cosmology and how we've just understood stuff, seemingly understood stuff so much more in the last 100 years, let's say, than in the past. Don't get me wrong; these people in the past they did some amazing math, but they were limited by their tools. Okay, their telescopes, their whatever instruments they used. They could only observe. They were limited by their observations. Their brains were amazing, and our brains are just as amazing. It's not like we're smarter. I'm not saying that. The biggest change we've had over the last 100+ years is technology. Okay, that allows us to see bigger, better, faster, more. And with that comes so much more data that we're using our brains to sort through. We've been able to measure distances to objects. We've identified what we thought were just, smudgy stars for some strange reason aren't actually stars. They're nebula, which are clouds of gas and dust. You'll learn more about them later. We realize that our star, the sun, is in the middle of a galaxy, and not just that, holy crap, there's thousands upon hundreds of thousands more galaxies out there. Again, with better telescopes came the realization that what was seemingly a single star was an entire galaxy. Okay, and things just got so big so fast. It was mind-boggling. And there were folks in the right place at the right time working with that data to get us. I used the word cosmology a minute ago. Cosmology deals with how the universe came into being, okay, and stellar evolution and all that stuff. And the more we saw, the more data we had to process, and these folks just ate it all up, and our knowledge base expanded immensely. Okay, so anyhow. One second here. It is still recording. Okay. Didn't look like my PowerPoint was still recording. Okay. So got a few slides left here. I know I've been doing these nice short 10 to 15-minute lectures. We're doing a 20-minute one here. It's still nothing like the good old days when I'd pop off 54 minutes at you. So I mentioned some words here just a couple minutes ago. I thought everyone knew what a galaxy was, okay, until one semester one gal was brave enough to raise her hand and say, "Excuse me, you've used the word galaxy 5 times in the last 5 minutes. What is a galaxy? And all of us teachers are guilty about knowing that you might not realize this, that, or the other thing about, whether it's an English class, sociology, geography, whatever. We just know something so seemingly fundamental to us that we forget that not everybody knows that. So, what is a galaxy? A galaxy is an organized grouping of stars, okay? And there's one day when you're bored, Google them. Okay, there's so many cool shapes out there. We talk as Earthlings, we talk a lot about spiral galaxies because that is what our galaxy is, the Milky Way. Okay, we live in the Milky Way galaxy. It's a spiral-shaped galaxy, so we take a lot of pictures with our telescopes of spiral galaxies because we want to learn about them. But there's a bunch of other cool shapes out there. And just a little foreshadowing, we went from I didn't even get into big picture mode here. Sorry. There we go. We went from geocentric to heliocentric, and let's jump to galactocentric, if I could make up a word there for a moment. Where are we really at? We're out here somewhere, okay? We're in one of the outer spiral bands of a fairly good-sized galaxy. Nowhere near the center of the universe, okay? And that's okay. That's okay. The world can still make sense that way. Another word we threw at you a couple minutes ago was nebula. Okay? Sometimes people say nebulae. A nebula, I mentioned, was a cloud of gas and dust. And here's a beautiful picture, one I should have wrote down what nebula this was. Again, some amazing things to Google. Mother Nature is an amazing artist. Google nebula one day, and you'll see so many cool ones. Crab Nebula, Cat's Eye Nebula, Eagle Nebula with the Pillars of Creation in it is one of my favorites. So it's a gaseous cloud. It's full of elements, okay? And they'll say, this is a little too poetic, but there's stellar nurseries and there's stellar graveyards. We're going to start with the graveyard part. Once a star explodes, stars explode, by the way. You've heard the word before. It's called a supernova. When a star explodes, it leaves behind a cloud of gas and dust. And what happens over time, and again, we'll get to this in lecture eventually, is this cloud will start to condense, pull together, and it'll turn back into a new star. And the cool thing about it is that stars themselves are only capable of making so many elements. Okay, our star, the sun, basically makes hydrogen into helium. Okay, and that's good because that's good for us right now. But as it starts to die, it goes through a whole bunch of changes. That's the stellar evolution I mentioned a little while ago, and it can make all the way up to iron. All right, and if you're familiar with the periodic table of elements, iron isn't very far. But when these things go supernova, when they collapse and explode, they create heat that is unimaginable. And it's through those stellar explosions that we've got all of the other elements that we currently have, at any rate, in our neck of the woods. And there's folks out there that study this stuff. And based on what they're able to understand, our star, the sun, is probably done this 3 times. Okay, in order to get the periodic table that we currently have, you would have had to have fused through 3 supernovas. And the cool thing I think about that is when this all goes down again, and our sun, another 5 billion years or so, our sun does this again, that we're going to get new elements. That's kind of neat. So, anywho, so that's a nebula. Okay, it's a cloud of gas and dust left over after a star explodes, and it makes new stars. Okay, so perspective. I think this is the last slide here, and I told you this a moment or so ago. We're not at the center of anything. Okay, we're in the outer arm of a spiral galaxy. And within our galaxy, just as a reference point here, our sun, okay, takes 230 million years to make one loop. So picture the sun in that spiral galaxy picture I showed you a couple minutes ago, and then picture the second hand on a clock making one lap. 230 million years, all right, for us to go around our galaxy. And what that means is that in the one loop, dinosaurs have been created, destroyed. The giant mammals have come and gone. Humans have risen, and we're doing what we're doing, all in one loop. Coincidentally, that takes us moving at 155 miles per second, which is 558,000 miles per hour. So you're moving pretty fast. I always tell people, don't feel so bad if you get a little discombobulated. It's a word we used to use a lot, where you just kind of like say, whoa, when everything doesn't feel right. You're moving, several different directions all at once, very, very quickly. Not only is the Earth rotating on its axis, but the Earth is rotating around the sun. The sun is rotating around the galaxy, as we just told you, at 558,000 miles per hour. But the Milky Way itself is part of a larger galactic cluster that is also rotating at its own direction, at its own speed. So you've got good reason every so often to get a little discombobulated. All right, and one more perspective slide there. I found that I had not seen this picture before. This is a really cool one. This is a view of the Earth and the Moon, taken from Mercury, all right, by the Messenger space probe. I did not grab a date on that. I apologize. But there you are. Take care, folks.